Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over question number 2 of the 2003 AP Calculus free response question. And this one focuses on position, velocity, and acceleration. All right, let's take a look at question number 2, the first part. It says a particle moves along the x-axis so that its velocity at time t is given by this velocity function right here. At time t equals 0, the particle is at position x equals 1. The A part, find the acceleration of the particle at time t equals 2. And then another question is the speed of the particle increasing at t equals 2? Why or why not? All right, before we get started with this problem, let's go ahead and write down some formulas that are going to guide our problem solving process. Formulas. The first one has to do with the connection between position, velocity, acceleration, and jerk. So we can call that Ziva XVA. So when you're going down, you differentiate downwards and integrate upwards. Okay. So if you're going from position, which is x, to velocity, what you do there is you differentiate once with respect to time. If you're going from velocity down to acceleration, you differentiate once with respect to time. If you're going from position all the way to acceleration, guess what? You differentiate twice. You find the second derivative of position. Okay? Now, when you're going down, you differentiate. When you're going up, you integrate. So if you're going from your acceleration to your velocity, you're going to find the integral of the acceleration plus v0, the velocity at the given start position. Okay, if you're going from velocity to position, you're going to integrate. Remember, you differentiate down, integrate up. You're going to integrate the velocity plus the initial position x sub 0. Okay, in this problem, you notice it stated here that at time t equals 0, the particle is at x equals 1. This can also be written as x of 0 is equal to 1. So if you're integrating from 0 to some other point of the velocity function, the constant or initial position is going to be 1, and that's what you input here. We're going to be using that later in this problem. Okay, so that's one formula you want to keep in mind, the connection or relationship between position, velocity, and acceleration. The other one has to do with the behavior of the speed. Is an object speeding up or slowing down? So this is an easy way to remember it. If your velocity and acceleration, if they have the same sign, guess what? You are speeding up. Okay, your speed is basically increasing. That's another way to say it. But if the velocity and acceleration have different signs, that means that your speed, the object is going to be, the speed is going to be decreasing or slowing down. So let's put it this way, speeding up or slowing down. Slowing down. Another word for slowing down is basically means that your speed is going to be decreasing, okay? Your speed is decreasing when you're slowing down, and your speed is increasing when you're speeding up. Okay, so these are the two points you want to keep in mind. All right, let's go ahead and answer the question. Find the acceleration at t equals 2. So what we've been asked to find here is we're to find a at 2. Okay, what are we given? We are given the velocity. So the first question you want to ask yourself is, what is the connection between acceleration and velocity? You look at this continuum we have here, we're going from velocity down to acceleration. And how do you connect them? By differentiating, okay? Acceleration is the first derivative of velocity. Okay, so let's write down the connection here. So A of t is basically d dt of the velocity function. Okay, or you can write it as v prime of t using a different notation. Okay, so if A of t is v prime of t, that basically means that A of 2 is the derivative of v evaluated at t equals 2, or you can write it as v prime of 2. Same, they mean the same thing. Okay, now if you're asked to do this by hand, there are two parts to it, but this is a calculator active section, so we are going to be using our calculators. Okay, but let's just do a real quick review on this, because they could ask this question in a non-calculator part of your FRQ. You never know. Okay, so if you're supposed to do this by hand, there are two steps. A of 2 will involve, first of all, finding the acceleration, okay, which is the velocity, the derivative of the velocity. And then the second part will be to evaluate the velocity at t equals 2, okay? So you do your calculus first before you do your algebraic evaluation. Calculus before algebra, keep that in mind. So v prime of 2. That's if we were to do this by hand. But we have a calculator, so we can execute these two steps simultaneously, or we can ask our calculator to do these two steps simultaneously by entering the following command. All you just simply do is you plug in the derivative of the velocity and evaluate it at t equals 2, and that should give you your answer. All right, so the sequence of steps we're going to be using to enter this problem into the calculator are as follows. First thing we're going to do is we're going to store the function in v of t. Okay, so we're going to store what the function is, which is negative t plus 1 times sine of t squared over 2. Now, when we start this in v of t, we don't have to bother entering it again. Okay, all we're going to work with is v of t after storing it. Okay, so having that after storing it, now we're just going to find the derivative of v of t. The independent variable is t, of course, so with respect to time. So that differentiates the velocity function and gives us the acceleration at any time t. But we want to evaluate the acceleration at t equals 2 seconds. So we're just going to evaluate the result at t equals 2. Okay, so we're going to have the calculator do two things for us: differentiate and then evaluate simultaneously. Okay, all right, so let's go ahead and take a look at how to do that. So let's first of all enter the function into v of t in the calculator. So negative t plus 1 sine t squared over 2. So we're going to store that in v of t. Okay, store that in v of t. Enter. The calculator will tell you done if you entered it correctly, and then you can go over your entry to make sure it's consistent with what the problem says. Negative t plus 1 sine t squared over 2. And if you want to just check to see if your entry worked, you can just and type into v of t in your calculator, press enter, and it gives you the function. So that's perfect. Okay, so let's go ahead. We're done with the first part. Let's go ahead and find the derivative. So we're going to find the derivative of the velocity function. Differentiating with respect to time, that's an independent variable. Okay, if I differentiate this, this will give me the acceleration function at any time. But I want to evaluate it at t equals 2. All right, enter. And we need a numerical result here, so we press diamond enter to get the numerical result. So that's our result right there. I'm going to have us carry out our answer to 4 decimal places. For the AP exam, your answer should be accurate to 3 decimal places, but I just carried to 4 for safety reasons, so you're going to mess up the 3rd decimal place. Okay, so we're going to write our answer as 1.5876. Okay, so that's what A of 2 is. First answer, A of 2 is 1.587.6. This is the acceleration as t equals 2. Another good practice is to always box your answer. It helps the reader to know where your final result is, and helps them to give you accurate scores. Okay, now we're not done with problem 1a. There's another question there. It says, is the speed of the particle increasing or decreasing? Why or why not? So we're going to be using formula 2 here. Speed increasing or decreasing, we're going to be looking at the signs of the velocity and the acceleration. So what we're going to do is we're going to look at what is v of 2. V of 2 is what? We already know that A of 2 is equal to 1.5876, which implies that the acceleration at t equals 2 is positive, is greater than 0. In order for the object to be increasing in speed or speeding up, the velocity must have a positive sign, okay? If it's 0 or negative, then we cannot conclude that it's speeding up, okay? So let's go ahead and do it. Now, the nice thing about storing things in your calculator is that you don't have to bother entering stuff over and over again. What I'm just going to do is I'm going to call up my velocity function, and I'm going to change the input from t to 2, v of 2. Okay, so what this calculator is going to do now is it's going to take 2 and input it into the velocity function. We need a numerical result, so press pound enter, and our result is 2.7279. So negative 2.7279. This means that the velocity at t equals 2 is negative. All right, so what's our conclusion? Since v of 2 is less than 0 and a of 2 is greater than 0, the velocity and acceleration have different signs, so it's like they're working against each other. So guess what? They have different signs, so the object is slowing down, okay? So the particle is decreasing in speed or slowing down. Okay, you can see one of the two, it means the same thing. It's decreasing in speed, or slowing down. They mean exactly the same thing. Okay, so just basically looking at the signs of velocity and acceleration at any particular time can tell you if the object is speeding up or slowing down, and if this formula here is to guide you through that process. Okay, so let's look at the B part. It says find all times t in the open interval 0 less than t, t less than 3 when the particle changes direction. Justify your answer. So we're going to be using a rule here. The rule is as follows. The direction of motion changes where the velocity changes signs. Okay, changes sign. All right, so the velocity goes from positive to negative. That means it's going from left. It changes direction from left to right. If it changes from negative to positive, that means it changes direction from left to right. Okay, so the sign of the velocity basically tells you the direction. So anytime you see the word direction, you're looking at the sign of the velocity. All right, positive is forward and negative is backwards. So whenever you have a sign change, you also have a direction change too. Okay, so what we're going to do is take a look at the velocity function and look at where it changes signs from on this interval 0 to 3, and those values will be where the particle changes direction. Okay, since we can use our calculator in this problem, we don't have to sweat it. We can just take a look at the graph to determine where this sign change happens. Okay, so we're going to graph graph the velocity function. Now we already have the velocity entered into the calculator, so what I'm going to simply do is in my y window, I'm going to type in v of x. Okay, enter. The independent variable here is x as indicated. So when I type in v of x, what the calculator does is it replaces all the variables on that velocity function into a format that's consistent with the independent variable that the calculator program uses, which is always x. All right, so you don't have to waste your time typing it all over again and put an x in place of t. All right, so we're going to graph the function. Wait a minute, let me do this. Let's do, let me make it a standard window first. So when you graph it, it's going to look like this. Standard graphing window. All we care about is from 0 to 3. Okay, so we're going to use our zoom box tool to zero in on, go from 0 to 3 to somewhere a little bit behind 0. I'm going to move the cursor high enough. This is 1, 2, 3. So I'm going to move the cursor high enough so that it captures the maximum and minimum of the domain of the function from 0 to 3. So press enter. That's the upper left corner of our window. And then move it all the way. Pay close attention to the x value. We want to make it slightly bigger than 3. Oh, okay, that's good enough. Let me get a little bit bigger. Okay. Press, and then you bring it down. So the rectangular box I'm drawing right there is what will be graphed after I press enter. So I have 0 to 3 looking good. Press enter. So I can block out all the noise and focus on the relevant component of the function that I care about, which is from 0 to 3. Okay. All right. So this is what we have. So now let's see what this velocity function, what does it tell us about the direction of the motion of the particle? Okay, so what I did is I grabbed a screenshot from the calculator. So this is 3 right here. So this is where we're going to stop our consideration of the function. Now, one thing you'll notice is that from 0, at 0, it's at rest. It's neither negative. It's not going back or forth, okay? And then this entire region right here, see that? What's the sign of the velocity? The sign of the velocity is negative. Okay, so all the way to this point, the sign of the velocity is negative. Negative, 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 negative. So what does that tell us? It tells us that from 0 up to this point right here, velocity is less than 0, so the object is moving to the left. Okay? How about over here? From the 0 all the way up to 3, up to this point. From here to here, guess what's happening? On that interval, the velocity is greater than 0, which means the object is going to the right. So the question is, what happens at this point right here where it's neither negative nor positive? This is where the sign changes. It changes from negative to positive. Okay? So this is where the particle changes direction. So let's go ahead and find out what that is. That is basically the 0 of the velocity function, okay, or the x-intercept. So we're going to find out what that is. Just press F5 and scroll down to 0, enter. The lower bound, we can put 2 or something to the left of this point of intersection. So let's just put 2. Enter. Okay, so the arrow is pointing to where the 0 is. The upper bound, pick a number bigger than that. You could use 3. Enter. And bam, there goes your t-value where the particle changes direction, 2.5066. Okay, so this value right here is 2.5066. So note, you have to be very careful when answering these FRQ questions. You are asked to provide justification. We cannot just say, oh, you know what, t is equal to 2.5066. We are not going to get full credit. We have to justify our answers. So all we just have to do, you don't have to write too much, okay? Just keep it brief and to the point. So you can just write since the velocity v of t changes from negative to positive at t equals 2.5066, the particle changes direction at this time also. Okay, so that's all you have to say. It changes from negative to positive, the particle changes direction. On the test, you can just make a nice little graphical sketch of your argument. You just want to put as much as possible. Put negative here, positive here, so that your grader can see your mathematical reasoning. With a graph, they'll give you full credit if you do it like this, all right? All right, let's take a look at the C part. Here we are asked to find the total distance traveled by the particle from time t equals 0 until time t equals 3. Okay, so let's write down the formula. There are two formulas you want to keep in mind, okay? One is position or distance from the origin, and the other is total distance, okay? This one is talking about total distance. Total distance can be thought of as a scalar quantity. Sign is not taken into consideration. Whether you're going back or forth, you're just looking at the magnitude of the move, okay? So for total distance, we're going to be calculating the integral from the formula a to b. So let me just make a real quick change here. So total distance on an interval, it will always give you an interval for total distance. So let's say from a to b is basically the integral from a to b of the absolute value of velocity. This absolute value just makes the negative distance, negative displacement is positive, so that we can add it to the positive displacement, because sign is of no consideration when you're looking at total distance, okay? We're just focusing on the magnitude of the number. So that's why you never want to forget that absolute value when you're looking for total distance traveled, okay? Another keyword to remember when you're looking at the formula is you're thinking of traveling, okay? If you're going from, let's say you're going from LA to New York and back, you look at the total distance. It doesn't matter if you're going forth or back or forth. You're looking at the total amount of miles that you traveled. That's what we're looking at here, okay? So this is a formula we're going to be using. In this problem, we're looking for the total distance from 0 to 3. Using our formula, we're going to be looking at the integral. We are accumulating the distances from 0 to 3. And we're looking at absolute value of velocity times dt, okay? So if you think about this, distance is equal to rate times time, okay? So this is like a rate, and this is like a time. You're looking at infinitely narrow accumulation of your distances over this time interval to give you a total distance, okay? So that's why it's set up in this format. So this is a simple calculator work. The only hard part is remembering your formula and entering it correctly in your calculator. we already have v of t stored in, so we're just going to evaluate the integral of, go to catalog, a, look for absolute value of v of t, close that. So that closes your absolute value argument. Variable of integration is time t, lower bound, lower limit of integration is 0, but accumulating all the way to 3, okay? It's diamond enter for to get an approximation, a numerical approximation, to give you some time to carry out the accumulation. Okay, wow, took a minute there. Anyway, so this is your answer, 4.3338. 4 decimal places, please. So 4.3338. That's the total distance traveled from 0 to 3 seconds. All right, let's take a look at part D. It says during the time interval from 0 less than or equal to t less than or equal to 3, what is the greatest distance between the particle and the origin? Show the work that leads to your answer. Okay, now there is a difference between this question and the previous one. What is the difference? This is not talking about distance traveled. It's talking about the distance between the particle and the origin. So guess what? We're looking at displacement here. Okay? This is displacement. So we want to look for what is the magnitude of the displacement. That's what we're looking at. How far to the left or right is it? You know, what's the biggest displacement from the origin? Okay? So since we're looking at displacement, which is a vector quantity, we're going to be using a different formula. All right, so let's take a look at the formula that we're going to be using here. So your formula is going to be a position formula, okay, displacement of position, basically the same thing. So x of b, position at x equals b is equal to the initial position, x of a, plus the distance traveled, this integral from a, the net change in position, okay? So you notice there's no absolute value here because this will calculate the net change. It does take into consideration the sign, okay? So you add the net change in position to the initial displacement, and that will give you what the position is at time t equals b. This is just your fundamental theorem of calculus part 1, okay? X of b minus x of a. This is exactly the same thing. If you think about what is the integral, so this is x of b minus x of a. That's equal to the integral from a to b of v of t dt. If you like this formula better, you can use it. These are exactly the same thing, only that I added x of a to both sides to generate this first equation right here. All right, so this is what we're going to be using. All right, so further distance from the origin on this time interval, we're going to call back our graph because we need to know what's happening all over that time interval, okay? So from 0 to 3, it looks like the object is going left, 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 left. Guess what? At t equals 2.5066, it changes direction and starts heading back to the right, okay? Now, they didn't make it back to the original position. They didn't make it back to the original position. Well, the only way we can know if it made it back to the original position and even exceeded and headed to the right is by looking at how far it traveled to the left, namely the integral here. Do you see this area right here? Tells you how far it travels to the left. And then this region right here, that integral will tell you how far it travels to the right. Okay? If this area is bigger than this one, then it's still to the left of the origin. Okay? If they're the same, that means it takes you back to the origin. If the positive area is bigger, that means it went past the origin to the right. So we know what the total distance traveled is, which is, we did that in a previous question. Total distance is 4.33 3.8. So how much of it was traveling to the left? So in order to figure out the total distance traveled to the left, we're going to take a look at the following integral. So to find that out, let's write that down. Total distance to the left, total distance to the left. That's basically going to be the integral from 0 to this point where it changes direction, because after that is going to the right. Okay, so to 2.5066 of your velocity. We don't care about adding absolute value signs here because this entire interval is negative anyway. There's no sign change to t. And we're also looking at just the distance traveled. Okay, so let's enter this into our calculator. We're gonna do the integral of our velocity function. Call this up, d of t. Independent variable was t, lower bound is 0, upper bound is 2.5. Well, you know what I can do? Let me call up the other answer just for accuracy purposes. Is it somewhere there? No, I don't have it. Okay. All right, so 2.5066. Okay, enter. I need a numerical answer. Okay, so there you have it, negative 3.2655. So negative 3.2655. Now, if you notice, this portion right here traveled to the left, negative 3.2655. This distance it traveled to the left is greater than half of the entire distance. Okay, so check this out. Since 3.2655 is greater than half of the total distance traveled, guess what? The object is still to the left of the origin. It didn't cover enough distance here. Just subtract it to know how much it traveled here. It didn't travel enough distance to the right to go make it back to the origin. Okay, so since this is the case, the particle is still to the left. Is still to the left. So the farthest distance, only farthest distance we're looking at is where it changes direction. Okay, so the farthest distance from the origin, distance from the origin occurs at t equals 2.5066. The question doesn't just ask us where is it the farthest. It asks us to find what is the distance between the particle and the origin. So we actually have to compute how far the object is. Okay, let me just give you a visual as to what's going on here. Okay, just a little visual on the movement of the particle so that it makes sense. Okay, so at t equals 0, guess what? The object or the particle was at the origin. Okay, and then it's oh sorry, I take that back. At t equals 0, it was actually to the right. It was to the right of the origin. It was 1 unit to the right. So at t equals like 1, 2, 3, 4. At t equals 0, it was somewhere to the right of the origin, 1 unit to the right. Okay. Then what happened? The object started to travel in the left direction. Okay. How do we know that the object started traveling in the left direction? If you take a look at the graph here, what does it show you? It shows you that it heads negative, the velocity is negative, so you're going in the left direction, so left, 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 okay? Keep heading left. And then at a particular point in time, the object changes direction, and starts to head back, okay? Somewhere here, it stops. This point in time where it changes direction, you know what the time is where it changes direction? At t equals 2.5066. And here is the other interval, t equals 3, okay? So the question is, what is the distance from here all the way to here when it was farthest from the origin, okay? Because it never had enough time to go here. So what's this distance? That's what we're looking for, okay? So we're basically looking at the position function because we're looking at how far the object is from the displacement from this position right here. Okay, so let's find the displacement from t equals 0 all the way to this time right here. Okay, so this displacement right here is just the position at t equals 2.5066. That's what displacement is. So we're going to look at x of position at 2.5066. Looking at the formula up here is equal to the initial position, x of 0, plus the distance it traveled, the net change in position. It doesn't matter if it's zigzag. We just want to know how far did it travel from here all the way to there, okay? So from 0 to 2.5066 of the velocity. Don't put absolute value there, okay? Or else you mess things up. So v of t, t, okay? Because the sign actually matters here because we're looking at net change in displacement. Okay, so all we do is just plug this into the calculator, but we're going to be careful because what is x of 0? We talked about that earlier. The position at t equals 0 is 1. So we're looking at 1 plus the integral from 0 to 2.5066 of v of t dt, okay? So this is what we are entering into our calculator. So we're going to do, oh, I already have part of it here. I'll just have to just add 1, yeah? Add 1 to my answer, or let's do this. I don't want to waste time because this calculator takes forever to evaluate the integrals. So just add 1, bam, and enter, bam. Okay, so that's the displacement. The displacement is negative 2.2655. So the position R066 is negative 2.2655. So what's the distance? How far is it from the origin? So the greatest distance from the origin is basically the absolute value of this result we got here. Remember, this is the position or displacement. We're looking at distance. So you just take the absolute value of the displacements, which is 2.2655. So this is how far to the left the particle went. That was basically the farthest displacement from the origin given the time interval 0 to 3. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP Calc exam, you give us a thumbs up. Your positive feedback is very valuable and supportive to us. If you have any questions or comments, just place it in the comment section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for the remainder of this review series. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day.